Hello everyone. Today we are going to study about half adder and full adder circuits. Half adder is a combinational circuit that performs the addition of two bits. The circuit needs two binary inputs and two binary outputs. The logic symbol of half adder is this one. Here we can see that inputs are marked as X and Y. Here we get the sum and here we get the carry. Truth table for this half adder is shown here. Here we can see that when X and Y are zeros, sum equal to 0 and carry equal to 0. When the inputs are 0 and 1, then sum of 0 and 1, it is 1. Carry for this one is 0. When the inputs are 1 and 0, then sum is 1, carry is 0. When both the inputs are 1, then if we add them, our answer is 1, 0. That means here the carry is 1 and sum is equal to 0. And from this truth table, we can see that when any of the input is 1, then the sum output is 1. If both the inputs are 1 or high, then only the carry output is 1. Boolean expressions for the sum and carry from the truth table for the half adder is S equal to X bar Y plus XY bar and C equal to XY. The set of equations we represent by 1. Then we can see that the output of this circuit S, that is equal to the output of a exclusive OR gate or XOR gate. So first equation we can represent by S equal to X XOR Y. And C same, C equal to XY. That set we represent by 2. From equation number 1, we can see that we can realize our half adder using AND gates and OR gates. So here the inputs are X and Y. Then connect one NOT gate to this input X. Then we get the input as X bar or X complement. Connect another NOT gate to this Y. Then the output will be Y bar. So here we have X, X bar, Y and Y bar as the inputs. Now connect X bar and this Y, that is our first term, X bar and Y to this AND gate, then the output will be X bar and Y or X bar Y. Then connect X and Y bar to another AND gate, then the output will be XY bar. Then connect these outputs to another OR gate, then the output will be X bar Y or XY bar, that is our sum. Then for getting this carry, use another AND gate and here we give the inputs as X and Y, then the output will be XY. So we can realize this first equation using this diagram. Then another way of realization is using an exclusive OR gate. Here the inputs given are X and Y, then the output will be sum. And if the inputs are connected to an AND gate, then the output will be X and Y or XY, that is our carry output. The full adder is a combinational circuit that performs the addition of 3 bits. It consists of 3 inputs and 2 outputs. 2 inputs are the bits to be added. The third input represents the carry from the previous position. So logic symbol is shown here. Here the inputs are marked as X and Y, third input by C in. And the output is marked by sum S. And the another output is CO or carry out output. Here the truth table is like this. Here we can see that the inputs are X, Y and C in. Outputs by S and C out. Here we can see that our sum output, that is 1, only one of the input is equal to 1 or all the inputs are equal to 1. And for this carry, it is 1 only when the 2 or 3 inputs are equal to 1. Here we can see that when 3 inputs are 1, then also carry is 1. And for other cases, when 2 of the inputs are high, then carry output is high. Karnaugh maps for sum and the output CO is shown here. For the sum, we know that the inputs are x and x can take values 0 and 1 and y c in can take 0, 0, 0, 1, 1, 1 and 1, 0 values. And when one of the input or all the inputs are high, then our sum is high. So here 0, 1 and 0, here we can see that the output is 1 or sum is 1. And for 0, 0 and x1, another 1. For 1, 1, that is C, y and c in 1 and 1 and x also 1, then we get another 1. And for y input 1 and all the other inputs 0, then again we get 1. So we can simplify the expression for sum using this Karnaugh map as x bar y bar c in plus x bar y c in bar plus x y bar c in bar plus x y c in. And for our carry output, same x values and y c in. And we can say that when two of the inputs or all the inputs are high, then only our CO is high. Then avoiding the overlapping, we can reduce the output CO as XY plus XC in plus YC in. We can realize full adder using AND gates and OR gates. So here we take the Boolean expressions as S equal to X bar Y bar C in plus X bar Y C in bar plus X Y bar C in bar plus X Y C in. And the expression for C out is XY plus X C in plus Y C in. So here the inputs are X, Y and C in. By connecting NOT gates to these inputs, we get X bar, Y bar and C in bar. Then take 4 AND gates. Here the inputs given as X bar, Y bar and C in. Then we get the output as X bar, Y bar, C in. For second one, inputs given as X bar, Y and C in bar. Then we get the second term. Then if we give the inputs like this, here we get the third term. Then for the fourth AND gate, the inputs are X, Y and C in. So the outputs of these 4 AND gates, they are given as the inputs for the OR gate. Then we get the output as this sum. And for getting the C out, here we need the inputs as XY, XC in and YC in. So we take X and Y here and this is the input for this AND gate. So output is XY. For another AND gate it is X and this Y bar. Third one, it is X and C in. And for third one it is Y and the C in. So Y and C in and X and C in. Then the outputs are XY, XC in and YC in. And we connect all the outputs to another OR gate. Then our output will be C out. So in this way we can realize a full adder. We know that the expression for sum is equal to X bar Y bar C in plus X bar Y C in bar plus X Y bar C in bar plus X Y C in. Now combine C in bar terms together. Then it is C in bar into X bar Y plus this X Y bar plus, now combine C in terms together. So it is C in into this X bar Y bar or XY. Now we apply De Morgan's theorem in second term. So it is equal to plus this first term plus the C in. Now we change the ands into ors and ors into ands. So C in into this x bar bar, that is x. Then this and is changed into or. So plus y bar bar, that is y, into this plus now we change into. So it is x bar plus this y bar whole bar. Then the third term it is C in into. Now we multiply this x with x bar, x bar it is 0. Similarly y bar is also 0. Then the other terms are x bar y and this xy bar. So it is C in into x bar y or xy bar whole bar. Now we can see that the sum equal to, here the first term C in bar, here it is C in. Here the second term is x bar y or xy bar, here it is x bar y or xy bar whole bar. So this is actually C in or this is actually x or y. So our S is now equal to C in or x or y. And carry output the expression is x bar y C in plus xy bar C in plus xy C in plus xy C in bar. So taking the C in outside, it is C in into x bar y, this term x bar y plus x y bar, this term. And the second one, take xy outside, so it is C in or C in bar. C in or C in bar, that is 1. So our carry output is now C in into x score y plus this xy. Therefore, a full adder can also be implemented using 2 half adders and 1 OR gate like this. For the first half adder, the inputs given are x and y, and here the output is S1 and the carry output is C1. And for the next half adder or second half adder, the inputs given for this exclusive OR are S1 and C in third input. Here the outputs are S, and the carry from this half adder it is C2. So C1 and C2 are given as the input for OR gate, and the total output, carry output, is taken as C out.